You've disabled sharing. Am I audible?
Yes, you are audible.
Can you give me the rights, please? Yeah, thank you. All right. Can everyone see the screen?
Yes, it's fine.
Perfect. Thank you. Okay. Give me a moment.
Yes. So very good morning to all of you in the third international conference on Advanced Communications and Intelligence System ICACIS 2024 day 2. So we'll start with our first keynote speech of the day with Dr. Navneet Kaur Popley. She's an assistant teacher, professor, and software engineer. She's also uh, student counselor of IEEE Victoria Educational Activities, uh, Faculty of Engineering and Computer Science, Department of Electrical and Computer Engineering of University of Victoria, Canada. So Dr. Navneet Kaur Popley will start with her topic, advancing AI method for addressing the impact environmental and anthropologic stressor on Canada's blue carbon habitats through enhanced secured underwater communication technologies. So welcome to you, madam.
Yeah, thank you.
Could you please
Thank you
start?
so much. Thank you so much, Dr. Ankush, and thanks to the entire conference team. I'm honored to be here, and I wish you best of luck for the entire conference. I'm sure it's going to be a great conference, and everybody will exchange a number of amazing ideas and will come out with great research for our economy. So as I was introduced, I am Navneet, and I am teaching in University of Victoria. I'm a software engineering professional. So I am doing a lot of research also, and my topic today is advancing AI-driven methods for assessing the impact of environmental and anthropogenic stressors on Canada's blue carbon habitats through enhanced secured underwater communication technologies. Now, seems to be a very, very complex topic, but actually it's not. It's a very, very important topic. And why I chose this particular topic was because, see, I'm living in Victoria. Now, if you look at the map of Victoria, we are an island. So we are surrounded by the Pacific Ocean in the same way as India has the Indian Ocean. In the same way, we in Victoria have Pacific Ocean around us. So though I'm a software engineer and I'm a licensed software engineer and I'm highly into tech, but you would know as tech researchers that it's very important to have interdisciplinary research. You cannot have a tech solution which is only a tech solution until unless it's linked to something which is a different discipline. So I'll tell you about my story before I actually move on to how I went through this particular topic. But before that, I would like to do my territory acknowledgement. That's traditionally the way we start every meeting, every conference, every speech, everything, because we are situated in the Lekwungen people's territory. So for that, I'm very thankful, I'm very grateful. So I acknowledge and respect the Lekwungen peoples on whose traditional territory the University of Victoria stands, and the Songhees, Esquimalt, and Wasanich peoples whose historical relationships with the land continue to this day. Thank you. Yeah, so we are Solids Lab. So when I talk about Solids Lab, SOLID stands for Software for Large-Scale Distributed Intelligent and Secure Systems. So this was a lab which was started by me. So I'm a PI of this lab. Currently, we have about 16 students with us. Some of them are masters, some of them are undergrad students, and we are working on different kinds of solutions. But basically, the lab has three main branches. So we have an AI ML branch, we have an embedded systems branch, and we have a cybersecurity branch as well. So I call upon all of you who are sitting there in India who are bright young professionals. In case you want to join us for a master's or a PhD or a postdoctoral program, go ahead, come to us. We're all ears for you. So I started this particular lab and I was very enthusiastic about it, and I wanted to solve a number of problems that we're facing today in the society. So I thought about how to, start doing different kind of projects. So I went to the geography department first. And the geography department, I have something called spectral labs in the geography department, and they're basically monitoring kelp in the underwater oceans. So kelp, if you see at these leaves, this is kelp. Kelp is basically an underwater plant. And kelp is particularly important for Canada's blue economy. So we created an image analysis system through which we could count the number of kelp plants, the number of sea urchins, the number of sea cucumbers, the number of sea stars. And through those analyses, we could tell whether the kelp population was increasing or decreasing, and we could give predictive analysis on the kelp health based upon the food chain that the kelp is moving in. So we showed this to a number of people, and we got amazing response for that. So now we're talking to the DFO. DFO is Department of Fisheries and Oceans in Canada. We're also talking to Kitselas of First Nations, which are an indigenous community in Canada. And we're trying to expand this particular kelp project to terrestrial organisms counting and analysis and prediction project as well. So we will now be expanding this project and we'll be thinking about counting and analyzing and predicting different kinds of fish and different kind of terrestrial mammals as well. We also went ahead and talked to the chemistry department, and we actually developed a chemistry sketcher for them. So this is for the students of the chemistry department, the undergrad students, the grad students, so they could practice their formulas in a paint kind of a structure. So this was a fun project, and it helped increase the learning of the chemistry students. Then we started developing small projects on oceans. So we developed a solar power ocean buoy, ocean pH monitoring device, a marine sentinel, which was detecting various oil spills. And we got funded from an organization called OceanWise to develop these projects. So when we were developing these projects, we realized that oceans is actually something which has to remain healthy for the economic health of our society. So it was at that particular time that we realized that a bigger project has to be created, which continuously monitors the stressors in the oceans. So we talked to the NRC. NRC stands for National Research Council of Canada. And we told them that we want to do a bigger project with you. So NRC and Solids, they shook hands together, and we've started building UCOMS. Now, UCOMS is an underwater communication secure sensor suite for monitoring of environmental and man-made stressors to know as to what is their impact on the blue carbon ecosystems. Now, when you talk about blue carbon ecosystems, many of you may not be understanding as to what what am I talking about. So, blue carbon ecosystems are, plants and mangroves and seagrass. So, all the underwater plants which have chlorophyll in them. So, chlorophyll is that green pigment which helps in the photosynthesis. So, all these plants, all these algae, the green planktons, all of these plants, when they combine together, they form the blue carbon ecosystem. Now, these blue carbon ecosystems can be actually impacted by things like increase of temperature or acidification, turbidity, salinity, etc. I'm sorry. So this was the project that we developed, and this is the project that I'm going to explain to you now. So what you see here for all the people who are embedded systems enthusiasts, they would know that this is basically the way sensors are laid down. This is called a data sheet for the sensors. So we had a number of sensors, and we created a sensor suite, and we mounted the sensor suite on our underwater drone. This is a Raspberry Pi that you see here. And we had a temperature sensor, a conductivity sensor, salinity sensors, chlorophyll sensors, pressure depth sensors, dissolved oxygen sensors, turbidity, pH sensors, etc. So this was our hardware embedded equipment, and our drone has a camera on it. So we ultimately want to combine our Ocean Eye image analysis project that I just showed you initially with this NRC project, so that we are able to get the information from the sensors, and we're able to get the images of the blue carbon ecosystems also, and we can combine both of these together to give us a better analysis. So what we basically do is that we have these sensors, and all these sensors are continuously monitoring the ocean data. Now, what we've done basically is, see, we want to test these sensors properly, and we want to know whether they're working as per our requirements or not. So what we've actually done is we've actually purchased 2 waterproof containers. So the kind of environment that we want the sensors to be working on is the Salish Sea. So what you see is Victoria, BC. This is where we are located. This is Vancouver, British Columbia. This is Seattle. And this is the Salish Sea that we are concentrating on. Now, the locations in the Salish Sea that we're concentrating on are the Discovery Passage, the Burrard Inlet, the Boundary Pass, and the Baines Sound. Now, for any researcher who's sitting here, they would know that it's practically not possible to take a boat or a ship or a ferry every time to places like Salish Sea and get your environmental sensor readings from there. So what we've done is we have purchased a container, and we've filled it with water. And we know what are the conditions of the various places in the Salish Sea are, as to what is the pressure, what is the tidal wave speed, what is the salinity, what is the pH, how much is the dissolved oxygen, and we know all these measurements. So we've tried to create the same kind of environment in our container in the water. And this particular array of sensors is also enclosed in a 3D printed waterproof enclosure. The drone is an underwater drone, so it'll not be destroyed by the tidal waves. It's a tethered connection right now, but we are trying to have a wireless drone too in the next iteration of the project. So what's basically happening is that we have the sensor suite and we have the sensor suite mounted on the drone. It is collecting these measurements continuously, but this is a data which we've been collecting since the past few months. Now, this data is not enough to train our machine learning model. So if you know, if you've done any machine learning on AI, you would know that if you want the model to be trained properly, you would need a huge amount of data. So if we want this model to give us good predictions, we want it to have at least 5 to 7 years of continuous data. So that was a problem that we were facing, that the drone data was not enough to train our model and it was not giving the right predictions for us. So we went to an organization called Ocean Network Canada. Now, Ocean Networks Canada, or ONC, is a subsidiary of UVic, and it has sensor suites which are all along the Pacific Ocean. And recently, it's moved to Antarctica and Arctic Ocean as well, and it's been collecting data since the past many, many years. So the kind of measurements that we were interested in, we took these measurements from 2016 to 2022. So all this data was collected in a database, which was on a cloud. So we have Arbutus Cloud, which was given to us by UVic. So the cloud resources were available to us. So we put all of that data in the cloud. But we realized that what happens is that ONC has sensors in Discovery Passage, Burrard Inlet, Boundary Pass, and Bain Sound, but sometimes some of the sensors just stop working. For example, the pH sensor, it stops working. So for example, for about 2 months, we do not have that particular data. What do we do then? So this was a problem that normally all databases will have. So we have an ETL, or extract, transform, load cycle for every database. So we had something called linear imputation, linear regression, linear imputation. So whenever we found that there was some missing data, we would impute that data and we would fill the missing values using, again, machine learning linear regression algorithms. So the machine learning algorithm will learn from the previous data and will predict the missing data. So through machine learning algorithms, we filled in the missing data, we imputed all the data. And after that, once we had the database, then we trained our spatio transformer model on this particular data. And we had the data from our drone also, which was continuously coming to this particular machine learning model. So through that, we were able to predict the role of anthropogenic sensors, which are basically man-made human stressors, and environmental stressors on blue carbon ecosystems. Now, what these stressors were, basically we were interested in climate change kind of stressors. So increased temperature, increased acidification, increased turbidity, increased salinity, or more, let us say, less dissolved oxygen. These were all human stressors or man-made stressors which affect the ocean environment. There are some environmental stressors also. For example, increase in the speed of the waves are environmental stressors. But mostly what we found was that the environmental stressors caused less stress on the ocean life and the blue carbon ecosystems than the human or man-made stressors. We were also able to find a correlation between what was the highest weighted sensor measurement here and how did it affect the blue carbon ecosystem. So we were able to find a relationship between chlorophyll and pH. So what we found out was that pH or acidification was the most weighted stressor in, in both human and ocean environment. So what we realized was that the temperature can increase, the conductivity can increase, the salinity can increase, but that does not affect the ocean health as much as increase in the acidification. And how do we get increase in acidification? We can get increase in acidification if there are oil spills happening, or if there are some manufacturing units which are pouring their polluted influx into the ocean. If there are a number of ferries which are running around, if there are a number of boats which are running around. So basically what is happening is, because of increase in pH, the amount of chlorophyll has decreased since the past 7 to 8 years. So the goal of this particular project is to continuously monitor the effect of man-made and environmental stressors on the health of the ocean, on the impact of blue carbon ecosystem. So we're able to advise the various factories, the various organizations, and we're able to tell them to reduce acidification so that the chlorophyll measurement increases again. This was just one part of the project. The other part of the project was security. Now, security is very dear to me because I'm a PhD in cybersecurity. I've done a lot of cybersecurity in my life, and the person in NRC who's our contact is a cybersecurity expert. So they wanted this particular application to be highly secure. Now, if you look at this application, you would find that this application is actually made up of three different parts. So if you look here, this is the physical asset, which is the ROV or the underwater drone. Now this underwater drone can be attacked. It's vulnerable. It's vulnerable to attack. The sensor suite, which is on top of it, is also a hardware device, and it's an embedded device. It's vulnerable. But if you look at the communications here, so if the ROV and the sensor suite is giving some information to the mainframe, for example, this communication can be vulnerable to attack. Then if you're doing some ML algorithm, some ML prediction, some ML analysis with data on the cloud, this particular communication can also be vulnerable. Not just that, this entire application is made up of both physical assets and software assets. So we have an entire software application which is also vulnerable to attack. So we have an auth service, we have an ingestion service, we have a data repository, we have WebSockets. So we have all these microservices and this entire software application and the entire database, which is also vulnerable to a number of attacks. So when you talk about these things, you actually open up a big can of worms. So for anybody here who's in cybersecurity, they would know this is a huge, huge task, Protecting an asset like that is a big, big task. But there was a question. I mean, why would anybody attack an ROV, for example, who's just monitoring a stressor? I mean, this is of no interest to a threat vector. And then we realize the kind of scale that we are moving into and the kind of political situation we are in. So with things happening in Israel, Palestine, everyone is in danger. So we don't just have a normal war happening, we can have cold wars also happening. So there can be a number of political adversaries who can actually attack you from different portions in your country. So for example, a nice use case can be if this particular application is scaled up, and let us say I have a federated learning internet of underwater drones. So let us say if I do not have one drone, if let us say I have, let us say, 500 drones, for example, who are monitoring my stressors. and I'm, let us say, monitoring my application remotely. And let us say this application is telling me that, well, the temperature has increased. So if the temperature has increased, you should do something to reduce the temperature. And let us say I have a mechanism wherein I can reduce the temperature by, let us say, giving a cold wave or putting a big piece of snow in that particular area so that the temperature reduces. Um, so what can happen in a big scaled application is that if this application is, let us say, attacked, and by the way, we were able to attack this application. I'll tell you how. But if this application is attacked and it starts giving wrong values or erroneous values to the mainframes, and if there are action items which are to be undertaken when a wrong value is given to them or any value is given to them, then a country can actually force another country to take an action which is actually not required. So, for example, if the entire sensor suite tells the mainframe that the temperature has risen, and the action item is if the temperature rises, a big piece of snow has to be dropped into the ocean at that particular place where the temperature has risen. Now, let us say if a country, let us say an adversary, has a missile at that particular
Ma'am,
place. Yeah.
sorry to disturb you. Our next speaker is waiting. So please conclude in a few minutes.
Absolutely.
Okay.
Sure.
Thank you,
Yeah.
sir.
So, yeah, no problem. So, yeah. So what I was just saying was this particular application has to be protected. So we've done vulnerability analysis, threat modeling, attack simulations, and defense strategies for this application. The last thing that we have actually done here is federated learning. So we have these drones which are working on their local data sets. They are training and initializing their data sets, and then they're giving their learnings to the mainframe too. So this finishes with my keynote. Any questions, anybody? Thank you so much for listening to me, and I hope you liked it.
Audience, any question? You can write in chat also.
Okay, I cannot see any question here in the chat.
Yes, ma'am.